This is part 5 of the series Circumference and Area, and in the last part we began with our discussion of regular polygons, and we're going to continue that discussion with a couple of more examples of calculating the area of regular polygons. So in this problem we're back to a regular hexagon, and we want to find the area of a regular hexagon, but this time that's all we're given is a radius. So as usual, what we're going to do is we're going to draw the bottom triangle, the representative triangle from our regular polygon, and draw in our apothem. Okay, now let's write in what we know. We're given a radius of 7. Now we know that the area of a regular polygon is 1/2 perimeter times apothem. Well, in this case, we are missing 2 entire sides. We're missing this whole side here, this side length, and we're missing the apothem. And that's all we're given is this side length. Now you may be thinking to yourself, I don't think we have enough information to solve this. But in fact we do. We're going to use the properties of regular polygons and all the information we've learned in the past to discern some new information which will allow us to solve for these 2 sides of this right triangle. Now, one of the key things we're going to need to do here is I want to show you, you don't have to do this when you're going through the polygon, the calculation, but I'm showing this as an example. I'm going to go ahead and draw a regular hexagon here just to exemplify what I'm talking about. Now we put in our center, and as I said before, we have one of these triangles for every side in the regular polygon. And all these triangles are congruent triangles. Well, that means if all of these triangles are congruent, then all of their corresponding parts must be congruent. That means this vertex angle of this isosceles triangle has to be congruent to this vertex angle, which has to be congruent to this, and this, and this, and this. And as you can see, all of those central angles, all of those vertex angles, add up to 360 degrees. So given the fact that all the triangles are congruent and these central angles are all equal, if we want to find one of those angles, that's all we really have to do is take 360, the number of degrees in a circle, and divide it by the number of triangles. And the number of triangles is the same as the number of sides in the regular polygon. In this case, 6. So 360 divided by 6 is just 36 divided by 6, which is 6 with an added 0. So each one of these central angles is 60 degrees. So this whole angle here is now given as 60 degrees. Now, given the fact that we have this triangle is an isosceles triangle, and this apothem is the perpendicular bisector of that base, you know that these 2 triangles are both congruent, which again makes this angle congruent to this angle. So if these 2 angles are congruent and they add up to 60, then you know that half of 60 is going to be the measure of this angle. Now, as you can see, with just doing this one little calculation here, we added a lot of new information. So what I'm going to do is I'm going to redraw this 30, 60, 90 right triangle, and we're going to work with that guy. So I'm going to redraw that down here. And again, your pictures don't have to be perfect. So this is 30, this is 60, and we know that this is 7. So we have to find this side and this side. Well, we can use our 30, 60, 90 relationships. Let's assume for the sake of discussion you remember those. We'll take a look at what you would do in case you happen to forget those, because we have an alternative. So in the 30, 60, 90 right triangle, the side opposite the smallest angle is always our smallest side. So this is A. The hypotenuse is 2A, and the side opposite the 60-degree angle is a square roots of 3. So that's the relationship of the sides in a 30, 60, 90 right triangle. Well, the thing we need to do to solve for these two sides is solve for a here. If 7 equals 2a, then we divide both sides by 2, and 7/2 equals a. So the smallest side is 7/2, and that makes this 7/2 square roots of 3. So now we have all of our information that we need to find the area of this polygon. So let's restate what we have. Area is 1/2. Well, our perimeter is this side length times the number of sides, 6. Well, this side length is going to be twice this side length, isn't it? Well, if this is 7/2, then this is 7/2 times 2. And if you take a look, 7/2 times 2, the 2's cancel out, that's just 7. So we know that this side length is now 7. So we'll write it in there. That makes our perimeter equal to 7, this side length, times 6, the number of sides. So 7 times 6 is our perimeter. And then we need our apothem. And we said our apothem is 7/2 square roots of 3. So we have 7/2 square roots of 3. Now we have to put all this into our calculator, and we get approximately 127.3 if you're going to one decimal place. All right, now let's assume for the sake of discussion that you forgot your 30, 60, 90 right triangle relationships. In order to solve for the apothem and for this length, that's all we're going to need to do is recall our trigonometric functions. So let's go ahead and put in a new triangle here, and we have the 30-degree angle and our 7 over here. We need the apothem, and we're going to call this side length x. Let's go ahead and find this side length. So we start at the angle, some old horse. Well, it comes right out as sine. So sine of 30 equals old horse, x over 7. Multiply both sides by 7. 7 sine 30 equals x, and we're going to store that value. Now let's do the apothem. Some old horse caught a horse. So cosine gives us the apothem. Cosine of 30 equals a horse. Multiply by 7. Multiply by 7. 7 cos 30 gives us the apothem. And we're going to store that value. Now, to put in our calculation, let's put in our calculation using these two values. And our area becomes 1/2 the perimeter. Well, the perimeter is going to be this side length times 2. Because this is our x right here. This is our x times 2 is this whole value here. Now don't get confused. Remember that this 7 came about because we knew our 30, 60, 90 relationships in this picture. So just kind of ignore those for now. But this x is this value is x times 2. So the perimeter is going to be 2x, which is this side times 2, times the number of sides, which is 6. So there's our perimeter times our apothem. And these are the values that we stored before. We put this into our calculator and we'll get this exact same result. Now, if you don't store this value and this value, you will not get this result. It will not come out the same. If you round this number and this number, you're going to lose precision and you're going to have some issues. So you need to make sure that you've gotten good at using the memory in your calculator before you can use these functions. All right, let's try one more example. All right, here we're looking for the area of a regular heptagon. Hepta, 7. Heptagon is 7 sides with a side length of 12. So without further ado, let's go ahead and draw our triangle. We have the apothem, and I need that value, and I'm going to need this value. Actually, they gave us a side length of 12, so I know that this value is a 6. So we can write that in right off the bat. We don't need our radius because it's really not necessary. That's all we need is our apothem. Now, if you wish, you could try to find that radius, but it's kind of pointless at this point. Now, we need this central angle because we need the measure of this angle because we're going to have to use our trigonometric functions to find that apothem. Well, we know that the sum of the measures of these central angles is 360, and there are 7 sides. So 360 divided by 7 is approximately 51.4, and this angle then is this divided by 2, which is about 25.7. Now, this is really crucial. You cannot use these numbers. You must take these values, or actually this value, and store it in your calculator. And I'm going to put this in C for central angle, just to have a value to put it in. You can write down whatever you want, but that's the number I'm going to use to refer to this angle. I'm not going to use the 25.7 because my answers would all be way off, because this number has a great number of decimal points after it. All right, now we start out to try and find this side. We know this side length, so it's sum. Old horse, nope, can't use it, don't have the hypotenuse. Caught a horse, nope. Taking oats away, it's tangent. Tangent of C. I'm just going to use C because that's the value that I'm storing in my calculator for the angle. So that's taking oats away. 6 over apothem. Now here we have to multiply by A. Multiply by A, so that's A tan C equals 6. Divide by tan C. Divide by tan C. So these go away, so it's A equals 6 over tan C. Now this I'm going to store as well. So now I have my C and my A stored. So this central angle and this apothem. So my area is 1/2. Area is 1/2 perimeter times apothem. That's 1/2. Now my perimeter is going to be, we were given the side length 12. So that's 12 times the number of sides, which is 7, times my apothem, which is the A that we stored. We put this in our calculator and we get approximately 523.3. Let's do a quick recap of the problem. We were given the side length. We found this by dividing this by 2. We had to find our central angle because we needed to use trigonometric functions to find the apothem. So 360 divided by 7 gives us this, divided by 2 gives us this. And because this is a decimal number, we had to store this in memory. So we set up our trigonometric function, tangent, taking oats away, and that gave us our apothem. When we calculated the apothem, we did 6 divided by the tangent of the value we stored in C here for this angle. And then we plug that in to our calculator, just as we normally would, and we got 523.3. I would suggest practicing these as much as possible. The more you practice these, the easier this process is going to become. All right, let's move on to the next topic, and we'll do that in the next video. So I will see you in the next video.